Hello physicists! Today we're going to be looking at a problem, probably my favorite book of all time, the Feynman Lectures on Physics. The problem is as follows. In chapter 1 of the Feynman Lectures on Physics, by the way, they're available online for free. Once again, they're probably my favorite physics book of all time. And if you're interested in having a read, check out the description for a link to the free online lectures. And anyway, so in chapter 1, he says that if you were standing at an arm's length from someone and each of you had 1% more electrons than protons, the repelling force would be incredible. How great? He asked. Enough to lift the Empire State Building? Nope. Enough to lift Mount Everest? Nope. The repulsion would be enough to lift a weight equal to that of the entire Earth. Now, my question to you is, was Richard Feynman right?
Well, of course he was right. We are talking about Richard Feynman, after all. However, let's see if we can prove that he is indeed right. Let's have a go.
Right, back to my digital whiteboard. The first thing that we need to do when we are tackling this problem would be to estimate the number of particles in a human body. After we do that, we're going to take 1% of that value, and this would give us the value of the excess charge on each of the people standing at arm's length. Once we have the charge, we'll be able to calculate the Coulomb electrostatic force between them, the electrostatic force of repulsion, and then we're going to compare this with the weight of the entire Earth. How exciting! Let's do this. Let's start off by estimating the number of atoms in an average person. For my assumption, I'm just going to take a couple of estimations. So let's say that the average person weighs 70 kilograms. Let's say that our density is very similar to the density of water. So I'm just going to presume that we have a 70 kilogram person that is made entirely out of water. This is actually not as crazy of an assumption as it sounds. We are about 60% water, and our overall density is approximately 10% higher than that of water, which is quite lucky because swimming is quite enjoyable. Anyways, so moving on, if a person weighs 70 kilograms, the molar mass of water is 18 grams per mole. So this means that there are 18 times 10 to the power of minus 3 kilograms for 1 mole, so per mole. All I need to do is just divide 70 and see how many moles I have, then multiply this by Avogadro's number. So 70 divided by 18 times 10 to the power of minus 3 is going to give me about 3,889 moles, and each of those moles has an Avogadro's number of particles. Remember, 1 mole contains an Avogadro's number of particles. So what I need to do next is just take that number, 3,889, and then multiply this by Avogadro's number, which is about 6 times 10 to the power of 23, is going to give us 2.33 multiplied by 10 to the power of 27. This is actually the number of water molecules. Well, in essence, each of them contains 10 electrons, so the total good estimate for the total number of electrons in the human body will be about 2.33 times 10 to the power of 28. So what I'm going to write down over here is, let's just zoom in a little bit more, is that each molecule will contain 10 electrons, like so. Some molecules in our human body will contain a lot more, so this is a relatively conservative estimate. Will contain 10 electrons, so our estimate for the number of electrons is going to be 2.33 multiplied by 10 to the power of 28. Let's multiply the number of electrons by the electron charge to find our excess charge on the two people. So what I'm going to do is multiply 2.33 times 10 to the power of 28 multiplied by the electron charge, which is 1.6 times 10 to the power of minus 19. This will give us 3.73 times 10 to the power of 9 coulombs. This is a huge number. Now let's plug this into our formula for electrostatic repulsion and figure out the force created by this excess charge. Remember, in this problem we essentially have two people which are about an arm's length distance apart. We're going to assume that the arm's length is approximately a meter for this problem, so the distance between them is 1 meter. Each of them have an excessive charge on them, which is only 1% more electrons than they would normally do. And let's say that this over here is Q. So this guy over here has a charge Q, and this guy over here has a charge Q. The question is, what will the value of the electrostatic force between them be? So we can find that using Coulomb's law, which I'm just going to write over here, that the force is going to equal to the magnitude of the charges, so Q times Q divided by 4 pi epsilon naught times the distance squared. Plugging in some numbers, we're going to get 3.73 times 10 to the power of 9, and we are going to square that. We are then going to divide this by 4 pi times epsilon naught, the permittivity of free space, 8.85 times 10 to the power of minus 12, times the distance squared, which is just 1 squared, which is 1. And let's put that into a scientific calculator. And we are going to get approximately 1.25 times 10 to the power of 29 newtons. Now this is a huge force. Now for comparison, the mass of the Earth is equal to 6.0 times 10 to the 24. So the weight of the Earth that Feynman refers to it, let's even take G to be a little bit stronger. Let's say that the weight will be equal to mg. So 6 times 10 to the power of 24 times 10, if we take G to be 10, will be equal to 6.0 times 10 to the power of 25 newtons. So surprise, surprise, Feynman was indeed right. The force created by the repulsion of just 1% excess electrons on the human body between two people a meter apart would be more than enough to lift the entire Earth, hypothetically speaking, of course. Absolutely incredible. Okay, physicists, I hope you have enjoyed this video. If there are any questions, do let me know in a comment down below. Thank you very much for watching, and please consider subscribing. See you in the next video.